This short video, folks, is on the normal probability distribution. The normal probability distribution is one of the most important distributions in statistics. It's important because it is so prevalent in so many situations. We can describe so many different distributions by this normal distribution. Another name for it that you know is the bell-shaped curve. And let's just think of some examples where the normal probability distribution can be used, right? So if we think about, say, times like athletes, say you're a sprinter, and you want to look at the, say, range of values of the sprint times for, some top athletes and so on, then what we might have is a situation where, if I were to draw this as a bell-shaped curve, now because this is time, the faster you are, the better. So this could be my bell-shaped curve. I have very few people that are really, really fast because this is a small amount of time. A few people that are considered maybe the slowest. And in the middle is where we have most of the folks running in terms of their performance times. So that's one example. Let's think about test scores. Test scores, we may have a few people who get really low marks, a few people who get very high marks. So if that's test scores, very high marks, very low marks. But the bulk of folks are somewhere in the middle. Now, sometimes we have skewed distributions where a couple of students get the marks so low that it skews the distribution to the left. But generally speaking, you would try to see a bell-shaped curve and so on. Amounts of rainfall. Well, in terms of rainfall, you could have periods, or even snowfall. We could have periods that have a small number of periods that have very high rainfall, a small number of periods that have very low rainfall, and then we have the bulk of the rainfall somewhere in the middle, or snowfall, if we want to consider that instead. So there's a lot of phenomena that can be modeled by the normal distribution. The normal distribution is a continuous distribution. And so because it is a continuous distribution, we are never interested in what is the probability of an exact value. We are always interested in the probability of a range of values. When we're dealing with a distribution, the random variable, or the variable that takes on values, we often denote it by x. So x is our variable. I will use small x to denote the value of the variable. So if we take a normal distribution, which is supposed to look like this, it has a mean, standard deviation, sigma. Some of the things we know about a normal distribution is that it is symmetrical, all right, bell-shaped curve, and because it is a continuous distribution, the probability of an exact value is 0. Now, why is that? Let's just think for a moment. The probability of x equal to small x. Well, because it is a continuous distribution, there is an infinite number of possible values, right? If we could divide up the scale into just into millions of something. So in that case, one value, if you remember the basic definition of probability, is the number of observations divided by the number of possible observations. Well, if the number of possible observations is infinity, that is essentially 0. So that's why we say that we're not interested in the probability of an exact value, but rather the probability of a range of values, such that if this were my x value, I'm interested in what's the probability of x being greater than or equal to small x. Notice small x is the value, big X is the variable. Or I could ask the question, what's the probability, I'm going to call this one x1, x2. I might be interested in what's the probability that x is less than or equal to x1. x2, sorry. not x1, x2. And then I could also be interested in what's the probability of being between x2 and x1. Because x2 is the smaller value, I'll have to go that way first. x2 and x1, right? So these are examples of ranges that we are interested in, okay? Now, if we wanted to find a probability using a normal distribution curve, we would need to know what we call the density function. In other words, what is this function right here, f of x? And to be able to calculate a probability, we would actually have to find the area under the curve. So if I say, what's the probability of x greater than or equal to x1? I would have to go, I'm going to integrate from x1 to infinity f of x d of x. So it's starting to look like calculus, right? So this will get complicated because the formula for the normal distribution is a crazy looking formula. Let me see if I have it here somewhere. There's what it looks like. We would have to integrate that formula. So far, you have not done integral calculus. You've done differential calculus in 1206, but not integral calculus. So we would have to integrate that function, but we are not interested in doing that. That's just a little too much work for us to take on right now. So how can we get probabilities using a normal distribution? And this is where z-scores come in. You may recall that we could convert all the values in a distribution to a z-score by simply taking every x value, subtracting the mean from it, and dividing by standard deviations. Remember, we did that earlier. If it is a sample, we would take x minus x bar and divide it by s. So we would actually find z-scores. The beauty about converting a normal distribution to all the values in a normal distribution to z-scores is that we would go from a normal distribution with a mean mu, standard deviation sigma, and when we convert it using this formula, z is equal to x minus mu over sigma, we actually get another normal distribution, because all we are doing is we are scaling. We are scaling from the normal. And recall that we said that z values were standardized values. So if this is a normal distribution, then this is a standardized normal distribution, or we just refer to it as a standard normal. A standard, I'm going to put it as STD, normal distribution. And it turns out that it has a value, a mean value of 0 and a standard deviation of 1. That's part of the characteristic of a standard normal probability distribution. Also, the beauty of it is that the area under the standard normal is equal to 1.0. And we know one of the things about probabilities, that one of the characteristics is that they must all add up to 1. So essentially, we can use a standard normal distribution to find probabilities if it is easy to determine what part of the standard normal corresponds to the part of the normal distribution that we are interested in. And by that I mean, what if I was interested in the probability of exceeding this value right here? Let's call it x0. Well, if I convert x0 to a z value, it has an equivalent value over here. We could call it z0. And so the area to the right of that z0 is the same proportion as this area is over here to the right of x0 to the normal distribution. The two things are related. Okay? So if it turns out that this area here is only, like, say, I don't know, 8%, 0.08, then it means the probability of x being greater than x0 over here, that shaded region would be 8% of the total curve. And so that's essentially a probability right there. The probability of x being greater than x0 would be 8%. So what we want to be able to do to find probabilities with a standard normal is to take any value from the normal distribution, convert it to a standard normal, and then see if we could find what proportion of that standard normal that z value is related to. And that gives us our probability. Now, why is that so cool or so important? It's because, fortunately for us, instead of having to do integral calculus to find normal probabilities, we have a table that gives us a z value. If we have a z value, it actually tells us the area under that curve. And that's how we find our probabilities. So the table would look something like this, where we have the z values, and the area that it will give us is the area to the left of that z value. So if I were to take a z value here, right, I'm looking for the area to the left of that z. This table will actually give us this value. So let's just pick one. Let's just say I'm just going to pick 0.94. If my z value is 0.94, I would have to look at the way the table is set up is that the first decimal place is in the first column and the second decimal place is in the rows over here. So 0.94, this would be 0.9, and then I have to go over to 0.04 to get 0.94, which gives me this area right here. So if my z value is 0.94, the area shaded in red over here would be 0.8264. So if that's the case, what is the area to the right of that? Because it all adds up to 1, we will simply subtract from 1. So this area would be 1 minus 0.8264, which is 0.1736. So that is 17.36% is the blue region, and 82.64% is the red region. So just knowing how to manipulate the table given z values will help us find probabilities. All right. So we're now going to go into sample problem, but I want you to make sure that you understand this particular table because we'll be using it quite a bit. So remember that the table gives us what we call the cumulative value under the table, or the cumulative area under the table, from before the z value up to that z value, that shaded region that I just showed you. And because the entire standard normal has an area of 1, to get what's to the right of that value, we simply subtract from 1. So having done that, now I think we're ready to take on a sample problem. Let's look at this problem in our workbook, and that is still workbook A. Workbook A ends with normal distribution, so I'm going to look at this particular question here as a start. Problem P646, that means the 46th problem in the textbook. But we have all the information right here. We don't have to go look for the textbook because I've got it right here. So here's the problem. I'm going to just make this a little larger so that you can see it more clearly. So we're told, assume that the test scores from a college admissions test are normally distributed with a mean of 450 and a standard deviation of 100. So mean 450 for standard deviation of 100. What percentage of the people taking the test score between 400 and 500? So those are the values of the variable that we would have to determine what's the probability of being in that range. Suppose someone receives a score of 630. What percentage of people taking the test scored better? What percentage scored worse? In a particular university, if a particular university will not admit anyone scoring below 480, what percentage of the persons taking the test would be acceptable to the university? So to be acceptable to the university, you would have to have a score of 480 or higher. And so we would have to make sure that we find what that probability is in that situation. So part A, I'm just going to write it out here so you can see, and I'll do the computation on the next page. So for part A, what we're interested in, I think blue will show up okay over here. So for part A, we are interested in the probability of test scores being between 400 and 500. So notice it's a range. It's not an exact value, it's a range. For part B, we're told, suppose someone receives a score of 630, what percentage of people taking the score scored better? So in that case, we are interested in the probability of somebody scoring better, greater than or equal to 630. And then part C, if the university would not admit anyone below 480, what percentage would be acceptable to that school? Well, that's part C, was basically saying you would have to have a mark of 480 or more. So I'm looking for the proportion of individuals who would have a mark greater than or equal to 480. So those are the 3 questions written out in probabilistic terms for you. And now we're going to actually go ahead and solve that. Okay. So let's write our information down. A notation that I'm going to be using throughout the course is that we could represent a normal distribution by putting n for normal, the mean, and the standard deviation of that normal distribution. So for our problem, it would be n 450, that's the mean, for standard deviation of 100. So we want to determine the probability of x being between 400 and 500. It is always useful to draw your diagram because then you can see the areas you're working with. So I like to draw it. The mean is 450. So I want to be over here and here. Between 400, I'm going to change the color. No, let's do this. So 400 and 500. So the area I'm interested in is this region right here. Right? Now remember, when we use our normal table, we get the cumulative values. That is from minus infinity up to the value of the z that we will compute. So one of the first things we're going to do to be able to find our probabilities is that we're going to have to now convert this to a standard normal. So that's how we work with the normal distribution. We convert the normal values to the standard normal. And how do we do that? We get standard normals by going x minus mu over sigma. Notice I'm not using x minus s over, sorry, s minus x bar over sigma. Is because the normal distribution given to us here is really the population, not the sample. All right. We did calculate z scores using samples earlier, but here we're dealing with the population. So in case you're wondering, how come we're not using x minus s x bar over s, is because we're dealing for population. So that's the population distribution. So we're going to have to convert this to a standard normal. And so just to kind of let you see the relationship between those, my graph may not be perfect, is that this, the 400 has a corresponding standard normal. We'll call it Z1. And then this one over here, the 500, has its also corresponding standard normal. We're going to call it Z2. So in essence, this is equivalent to the probability of Z being between Z1, and notice now my random variable for Z is big capital Z, and my values are small z, just like I had capital X and small x, Z2. All right? So that's the equivalent. So I must now find Z1 and Z2. Let me just write this out one more step for you so that way you could just see what I'm about to do, but I may not actually put that much detail the next time around. Is that we know that Z1 will be x1 minus mu over sigma z, and then Z2 will be x2 minus mu over sigma, where this would be my x2 and this would be my x1, right? So x1 gets converted to z1. x2 gets converted to z2. Both of them by using the standard normal formula. Okay? That's how we do that. Okay, so let's go ahead and find that for this particular problem. So let's find z1 would be 400 minus 450 over 100. This would be negative 50 over 100, which is negative 0.5. That's what that is. Let's find z2 would be 500 minus 450 over 100, which is basically 50 over 100. So it is positive 0.5. Those are the z values. Now, in cases like that, when we get these values that look like they're fractional, we might confuse that with a probability. It's not a probability, so don't confuse it with a probability. That's the z score. And so now we have to go to the table to find our relative, with our appropriate z values. So let me just write this out to show you now essentially what we have, which is the probability of x being between 400 and 500 is the same as the probability of z being between negative 0.5 and 0.5. That's what that is. And now we must go to the table. So let me see if I have my table handy over here. I thought I brought it in, but I'm going to pull in the table right here for us to see. So give me a moment. Let me bring that in with my handy dandy tool over here, bring in a file, and I go to my Google Drive, and we need our tables. And I need the Z table, so I'll import that. So there we go. So remember our Z values were negative 0.05 and positive 0.05. So what will we get if I look up negative 0.05? If I look up negative 0.05 in the table, I'm going to just shade that yellow. I will get this region right here. So that's negative 0.05. Sorry, that's not negative 0.05. Negative 0.5. My bad. And positive 0.5. Okay. So when I look up this area, I mean the area with this Z value of negative 0.5, I will get the yellow region. Now, if I look up the area associated with this Z, 0.5, let me see what color I haven't used yet. I'm going to do this as black. Then my table will give me all of this, because remember it's cumulative, right? So how do I get the green region? Notice that the black region includes the yellow region. In other words, this piece right here, I'm getting a little crowded. This includes the yellow region. So if I want to find the green section, just reminding you what it is this section right here, I must subtract the yellow region from the black region, and that gives me the green region. So that's what I must do. So this is equal to the area associated with 0.5, subtract the area associated with negative 0.5. Okay? That's what I have to find. So let's go find those values right now. So I need to find 0.5. So if I look over here in my table, I'm going to use red, makes it easier to find. So I'm going to expand this so you can see it. So you notice again, if you look at the diagram, it's telling us that when we look at a Z value, we get the cumulative probability, which is the blue region up here. Right? I mean, I'm painting it red, but it's supposed to be blue over here. All right? Cumulative probability. So I'm going to look up 0.5. And 0.5, folks, is actually right here. The first decimal place is right here, 0.00. So it's basically 0.50. First decimal place 0.5 in the first column. Second decimal place is over here. And so therefore the area, that cumulative area is 0.3085. But I must also look up positive 0.5 as well. And if I look at positive 0.5, it is over here. I'm going to expand this so you could see it. So first decimal place in the first column, second decimal place is over here. Right? And so therefore, this is the area, cumulative area, when the Z value is 0.5. So now I must subtract from that the area associated with negative 0.5 from the area associated with positive 0.5. So 6915. Let me go back here. So my answer to my question is, this is equal to 6915 taken from the table to 30, if I can remember it, 85. And so if I subtract that, 5 from 5 is 0. I'm just trying to do some mental arithmetic here, but it doesn't always work for me. So I'm looking at 0.3830. So my answer is the probability of X being between 400 and 500 is 38.30%. And that's the answer. Okay? So about 39% of individuals will have a score between 400 and 500. It's cool. Let's do the second part of that question. If we go back, what was the second part? What's the probability that X would be greater than 630? So that means somebody gets a score greater than 630. I'm going to squish that some more. Let me see if I could squish everything. Not quite. Time for a new page then. B. The probability that X is greater than or equal to 630. So it's the same as the probability of Z greater than or equal to some Z value, which is equal to, that Z value is 630 minus 450 over 100. So what I've done is I've just gone ahead now and said, okay, I know that it corresponds to a Z value, but that Z value is really 630 minus 450 over 100. Let me just draw the diagram so that you could see what I'm doing. This is 450, standard deviation of 100. The mean is 450. Let's color that. So here is my 630, and I want this probability right here, which means that there's a corresponding Z to this X. This is an X value from the normal distribution, and so therefore there is a corresponding Z value. Right? And we go from X to Z. How? Z is equal to X minus mu over sigma. And that's where this comes from. Good. Let's find our Z value. 630 minus 450 over 100. That should be easy enough. That's 180. 180 over 100. It gives us a z value of 1.8. Now let's go look that up. When we look up 1.8, remember we're going to get the cumulative value up to the 1.8, but we are interested in the values beyond 1.8. So this is 1.8 over here. Our table will give us this area to the left of 1.8, and to get this area we'd have to subtract 1 minus whatever this area over here is. So the area 1.8 would be this, and we'll have to subtract from the area 1.8. Let's find what that 1.8 is. We got to go positive 1.8. So here's 1.8 over here. 0.9641. 0.9641. So this is 0.9641. When we subtract 1 minus 0.9641, we'll get 0.0354. That's what we should get. So summarizing our problem, probability of x greater than or equal to 630 is the same as the probability of z greater than or equal to 1.80, which is 1 minus 0.9646, which gives us 0.0354, and that's our answer. Good. Let's do the last one. We were asked what percentage of individuals would be acceptable to that university. So we want the probability of x greater than or equal to 480 is what we're looking for in that case. Let me see if I could squeeze it on this page right here. So part C, the probability of x greater than or equal to 480, because only if your score is greater than or equal to 480 that you'll be acceptable to the school. So same idea, be the probability of z greater than or equal to some z value, which is equal to x minus mu over sigma. In that case, our x is 480 minus 450 over 100. Let's find the z value. Is 480 minus 450 over 100. That's basically 30 over 100, 0.3. So now if we look up 0.3, the area associated with 0.3 would be the cumulative area up to the 0.3. What we're looking for is 1 minus that. So our probability of x greater than or equal to 480 is probability of z greater than 0.3, which would be 1 minus the area associated with 0.3 or 0.3, and that is equal to, let's look up our table. Here's 0.3. Because there's no second decimal place, we stick with the first column, and so that's 0.6179. 0.6179. Going back here. So that's 1 minus 0.6179, which is 0.3821. So our answer to this question is 38.21% of the students will be acceptable. Okay, there you go. And that is how we solve this particular problem. So the normal distribution is actually quite an interesting distribution, and we could have fun calculating our probabilities with it. Let me see if I could start one for you and then get you to finish that. We have another problem. Let's see here. Problem 647. I'm going to just let you just read. I'm going to read this for a moment, and then we will maybe just do a part of it, and I'll let you finish it up. Okay. So here we go. 647. All right. So according to the National Association of Colleges and Employers, the average starting salary for new college graduates in health sciences is $51,541. The average starting salary for college graduates in business is $53,901. Assume the starting salaries are normally distributed and that the standard deviations for the starting salaries for new college graduates in health sciences is 11,000, and that for the standard deviation for starting salaries for new college graduates in business is 15,000. What is the probability that the new college graduate in business will earn a starting salary of at least 65,000? What is the probability that a new college graduate in health sciences will earn a starting salary of at least 65,000? What is the probability that a new college graduate in health sciences will earn a starting salary less than 40,000? We could repeat it as well for business if we want to. So we could just kind of play around with this. How much would a new college graduate in business have to earn in order to have a starting salary higher than 99% of all starting salaries of new college graduates in health sciences? All right. So how much would a new college graduate in business have to earn to have a starting salary higher than 99% of all the starting salaries of new graduates in the health sciences? Okay. All right. So let me start off with part A and let you take a look at that, right? So part A, we're being asked for what is the probability, let's go back here again, that a new college graduate will earn a starting salary of at least 65,000, right? In business, that is. So the first thing we should do is put down the information that we're given for each of them. And let me just get that written down properly. Sorry. So here we go. So for business, the distribution is normal with a starting salary of 53,901 with a standard deviation of 15,000. In health, it's normally distributed with a starting salary of 51,541 and 11,000 as the standard deviation. So first question, part A, what's the probability that a business student, and I'm going to just put X business just so that we could differentiate between them, will have a starting salary at least $65,000. So that's the probability, in this case, of Z being greater than or equal to the Z value, which is X minus mu over sigma. Well, what is our X? 65,000 is what we're interested in. What is the mean for business? 53901. And what's the standard deviation? 15,000. So let's find that Z value. Z is equal to, when we go ahead and we compute that, rather than rewriting that again, I'll just tell you that it is equal to 0.74. That's what the Z value is. So therefore, we are interested in the probability of Z being greater than or equal to 0.74. Now, because we're interested in the probability of exceeding 65,000, remember that the Z table will give us a cumulative value up to Z.74, but to exceed, we would have to get greater than 0.74. So therefore, we'd have to subtract from 1. So that would be equal to 1 minus the area associated with 0.74, which is 1 minus, and we got to go to our table, 0.74. Here's my first decimal place right here. My 0.4 comes over here. So if I come along, it would be 0.7704 would be that area. .7704, and so therefore that answer is 0.2296. So that's your answer. 22.96% of graduates will start more than $65,000. If you want to see what that looks like on the curve, and it doesn't hurt to draw it, this is 53,901. That's our mean. Our standard deviation is 15,000. And so we are interested in 65,000. And that's the area that we found. And we went and found the standard normal. And then with the standard normal, we were able to compute that the area to the left for the standard normal, this area corresponds to 77.4%, 0.04%. And therefore the area to the right is 22.96%. So almost 23% of graduates will start higher than the $65,000. Part B is computed very similarly, which is we want now to do the same thing for the health sciences. All right. So what's the probability a new college graduate in health sciences will earn 65,000 or more? So we just write that out as Px greater than or equal to 65, which is equal to Pz greater than or equal to Z, which is equal to 65,000. But notice now we got to use a different mean, which is the mean for health sciences. Well, I should put H over there for health, because I use B for business, so H for health. And this gives us 51,541 over 11,000. Okay, 11,000. And you should get a Z value when you compute that, a Z value of 1.22. So with a Z value of 1.22, we are looking at the probability of Z greater than or equal to 1.22 is 1 minus the area associated with 1.22, which turns out to be 1 minus 0.8888. So all you'd have to do is to go to the table just to verify that. If I look up 1.22, 1.2 is here, the second decimal place, 22. That's where I get this value from. And that gives us an answer of 0.1112, which is 11.12%. So 11% of graduates in health sciences will start off with a salary greater than 65,000. 23% for business will start off with a salary greater than 65,000. So that's how we would actually compute those values right there. I want to let you do part C by yourself, and I want us to also figure out the very last one, which is a little more interesting. So part C is easy to do. Let's just go back to what part C asks us again. This question: what is the probability that a new college graduate in health will earn a starting salary less than 40,000? Right? So essentially this question is asking us, that's part C, what's the probability will earn less than 40,000. And just got to make sure that, was that business or health? Let me just double check again. Health. So the probability health, and that is just PZ is less than or equal to some Z value, which is 40,000 minus the 51. I moved to a new page, so I don't have my values right in front of me. 51,541 over 11,000. All right, the Z value in this case turns out to be negative 1.05. And so then the negative 1.05, I'll show you how we get the value directly from the table. So this is 0, the standard normal, negative 1.05. And since we are interested in being less than this value, we don't have to subtract from 1. Because to subtract from 1 is to get the values to the right of the Z value. The table gives us the value to the left of that Z value. So if I go to negative 1.05, negative 1.0, and then 5, I got to come over to the fifth, 0.05 over here. I will get 0.1469. 0.1469. So that is the area that I'm actually looking for. I don't have to subtract from 1. So the probability of X less than 40,000 is the same as the probability of Z less than negative 1.05, which is 0.1469, which we got directly from the table. And that's it. So the very last question I want to do now, it says here that how much would a college graduate in business have to earn in order to have a starting salary higher than 99% of all salaries of new college graduates in health sciences? I believe there's an error in this question. It should have said a new college graduate, because we're going across distributions. We need to stick to one distribution. So that should have been, how much would a new college graduate, let me just go back to the question so you can see it. This question right here, how much would a new college graduate in business have to earn in order to have a starting salary higher than 99% of all starting salary of new college graduates in health sciences? Well, we went from business over here to health sciences over there. So I'm assuming that this should be health sciences here. We got to stay with one distribution, or we make both of them business, whichever one we want to do it. So I'm going to do health sciences, and I'm going to ask you to repeat that question, but with business. So how much would a new college graduate have to earn in order to have a starting salary higher than 99%? Higher than 99% of all the salaries. So that's an interesting question. So essentially, part D is saying that there is a starting salary, we'll call it just XO, just to differentiate them, so it's unknown. We have a starting salary for which the probability of making more than that, right, is 99%. Okay? The probability of making more than that is 99%. So let me just make sure we read that again. Oh, sorry. No, not the probability. That, I got to get this correct. Okay? So how much would a college graduate in business have to earn in order to have a starting salary higher than 99% of all the salaries? Okay. So basically, it's the other way around, which is all the other salaries are less than that. 99% of salaries are less than this particular starting salary. In other words, your salary is so high that 99% of the salaries are less than that. So if I were to draw this graph, it would look something like this. This is the salary that I'm making, or the college graduate is making, sorry. And 99% of all the other salaries happen to be lower, right? The way in which it's phrased is that it is higher than 99% of all the other salaries. So if it is higher than 99% of all the other salaries, this area to the left of it is 99%. The area to the right of it is 1%, 0.01. So that area right here, which I will shade in the green, 0.01, and the area in blue is 0.99. 0.99, which is okay. So let's find that. So what happens is that there is a Z value which corresponds to having 99%. To the left of it, we have to find that Z value. So there's a Z value that corresponds to this X value. So here's what we got. Less than Z, which is equal to X, O, which we don't know what it is, minus the mean, and since we're dealing with health in this case, right, 51541 over 11,000. But that is equal to 0.99. Okay, so we got to study this very carefully. The probability of making less than that amount of money is 99%. That means that that salary is higher than 99% of all the other salaries. Only 1% of the salaries are higher than that amount, right? So there's a corresponding Z value for which all the other Z values are less than that. And the probability of all these other values, Z values being less than that, is 99%, 0.99. So what we have to do now is go to the table and find this Z value, which has a cumulative value of 99%. So let's see if we could find that. Which Z value has a cumulative value of 99%? Since we're looking for 99%, we wouldn't look here because these areas are less than 50%. They're below the zero. These areas, the cumulative probabilities here, are less than 50%. So that's not what we're looking for. We have to look over to the right side. So we have to look to the next page. Those cumulative probabilities are greater than 50%. So we're looking for 99%. Now remember, that's the probability or the area. So to find that area, we have to look in the body of the table. We have to look in here, in the body of the table, not where the Z values are. We have to figure out what the Z value is because we don't know what it is yet. But we know that 99% it should be that shaded region. Well, let's find the closest value that we can to 99%. And the closest value that I find to 99% is this value right here. .9901. We're not going to get it exact, but we get as close to it as possible. That .9901 has a Z value of 2.33. So the Z value, which corresponds to having 99% of the curve below it, is 2.33. And that's what we're going to work with. So we have 2.33 is equal to x0 minus 51541 over 11,000. So with that, we could actually do some manipulation to solve for x0. We have the Z value, we have the standard deviation, we have the sample mean, not the sample, the population mean. All we need now is to find x0. So if we manipulate the formula and then make x0 the subject of the formula, we'll get x0 is equal to 51541 plus 2.33 times 11,000, which gives us an answer of, doing the math on that, $77,171. You could do the math to verify it. So, folks, to have a starting salary which is higher than 99% of all the salaries, you have to be making $77,171 as your starting salary. So that's the answer to this question right here. I would like you to do for me the very same thing and figure it out, which is not in the question, but I'm adding it right now. So what is the same thing here for business students? What salary do you have to make? Okay. So that we will now, I'm going to, instead of using 99 because you would already have the Z value, I'm going to give you 95%. So in other words, what starting salary would you have to make as a business graduate, which will be higher than 95% of all the starting salaries? All right. So you could finish that off for me. You know that it would be Z less than Z equal to X0 minus, I believe it was 53,901, 53901 divided by 15,000. Good. I'll let you finish that question off. So there we go. I think that sets us up with the normal distribution. Normal distribution is very powerful, very useful, because it is very prevalent in statistics. And so we will find ourselves using it quite a bit as we get into the other chapters in the text from chapter 7 onwards and so forth. So normal distribution is a continuous distribution. It has a density function, which looks a little crazy. To find probabilities under the normal distribution, we are only interested in ranges of values, not exact values, because it is a continuous distribution. For continuous distribution, the probability of an exact value is 0. So therefore, we are always focused on getting a range of values. To calculate the probabilities, we would have to find the area under the curve. But instead of having to do that, we can use the standard normal. You may recall a standardized value is to take the value, subtract the mean from it, and divide it by standard deviation. So it's really your x values expressed as standard deviations, which we call Z. Z is a standardized value. So when we take all the values from a normal distribution and convert them to Z values, we get a standard normal. The standard normal has the characteristic that its mean is 0 and the standard deviation is 1, and the area under the curve is also 1. We know probabilities add up to 1. So because the two distributions are basically identical in shape, and one is a scaled version of the other, if I identify a proportion on the original normal distribution, a part of that distribution on the original normal distribution, it corresponds to a specific or similar part on the standard normal. If I know the size of that part on the standard normal, then I actually have the probability. So all we're doing is converting the portion that we're interested in on the normal distribution over to the standard normal. And because the standard normal adds up to 1, any part of that standard normal will be less than 1, like 40% or 30% or 15% or whatever. So those percentages are indeed the probabilities that we're looking for. Because what is a probability? It's what the proportion of the whole is that our area of interest corresponds to. So if our area of interest corresponds to 0.15, our probability is 0.15. If our area of interest corresponds to 0.36, then 36% is our area. If our area of interest corresponds to 0.75 on the standard normal, then that is our probability. So folks, hopefully that gets you started. Thank you. And we continue on with chapter 7, sampling distributions.